Greetings and welcome to our uh, next installment of our Ask the Expert series, focused today on silicon carbide in high-powered electronics. I am Dina Ingram, and I am the marketing manager hosting today's event. Prior to hearing from our two experts, I would like to go over a few housekeeping items with you. All attendees have been muted. However, if you have additional questions that arise during the presentation, please ask them in the questions panel located in the bottom right corner of your screen. If time permits, we will try to answer these questions during the Q&A at the end of the presentation. Thank you to all of those that have pre-submitted questions. We have received a lot of questions and unfortunately are not able to answer all of them during the live webinar today. However, your questions are important to us, and our team will be following up with the answers in the coming weeks. Lastly, at the end of the presentation, you will receive a short 5-question survey about today's event. Feedback is a gift and is greatly appreciated. So please take 5 minutes to answer our short survey. Now, I will turn it over to Wee O, Senior Principal Scientist, who will be moderating the event today. Wee?
Thank you, Dina, for the introduction. Hello, everyone. I understand we have a big virtual crowd out there today. Thanks so much for joining us. As Dina said, my name is Wee O, and I want to start with a brief introduction of our expert team, followed by some background about our company. And then we'll launch into answering questions about high-power silicon carbide electronics. I am the moderator for this session. I've been with EAG since 1996 here at the New Jersey laboratory. It is my pleasure to introduce our experts, Drs. Peter Dzau and Jack Lee, both with the Northern California laboratory. Peter has been with EAG since 2004 and Jack since 2013. Therefore, among the three of us, you have over half a century of SIMS experience covering this session. A summary of today's agenda. Sorry. I will provide an overview of EAG Laboratories, then we will get right into what you came here for. Answers to your submitted questions regarding silicon carbide power electronics. If time permits, we'll try to tackle additional questions generated live during the session. Just a quick reminder that this session is being recorded, so you don't have to take notes, as you can replay its content at a future time. To kick things off, an introduction to our organization. Eurofins is a global leader in testing with more than 58,000 employees, 900 laboratories in 54 countries. Eurofins EAG is a division of Eurofins specializing in materials testing with over 40 years experience. We have more than 1,000 employees in 20 laboratory facilities all over the world. We have more than 2,500 different types of testing equipment and support over 5,000 clients. We just increased our battery capabilities at our labs in Sunnyvale and Syracuse. If I had to describe EAG Labs in 2 words, it would be problem solvers. As highlighted in this flow chart, EAG helps to solve commercial challenges from concept all the way through a product's life cycle. Client success requires control and optimization at all stages. We can help with R&D, prototype development, pilot studies, manufacturing, reliability, and failure analysis. EAG provides the knowledge and appropriate tools to help clients faster and better. Oh, sorry. Sorry about that. My apologies. For all the industries shown here, our highly skilled employees use industry-leading state-of-the-art technology and take advantage of scientific and engineering know-how to accelerate innovation through creative problem solving, objective analysis, and expert interpretation of data. Ooh. Let's look at our smart chart. SMART is an acronym for spectroscopy and microscopy analytical resolution tool, and it shows the technique we have at EAG, the techniques we have at EAG. This chart allows us to compare the spot size and detection limit of each technique. The x-axis at the bottom shows the range of spot sizes ranging from 1 centimeter at the right all the way to 1 angstrom at the far left. The y-axis shows concentration either in atoms per cubic centimeter along the left axis, in atoms in atomic concentration, or in atom concentration along the right axis in 100% at the top, down to 10 parts per trillion at the bottom. So within the box, you can select a technique based on the detection limit you need and the size of the area of interest. Please note on this chart, the box for dynamic SIMS, as this is technique our expert will touch on exclusively during the session. The advantage of this technique lies in its high sensitivity down to the part per trillion level at a moderate spot size in the upper micrometer range. With this foundation in mind, let's get right into the topic of interest, silicon carbide for high power electronics. For that, I'm going to turn things over to our expert, Jack.
Hello, Wei, thank you. My name is Jack Lee, a senior scientist from SIMS department. Today, my manager, Peter Zhao, and I will focus on the questions related with SIMS. So I will give the presentation, and my manager, Peter Zhao, will answer additional questions you may have. So here are some questions related with the silicon carbide properties. Silicon carbide versus fluorescent silicon. What are pros and cons? Which one is preferred? Doped silicon carbide or pure silicon carbide? Why is silicon carbide better suited to high voltage applications than silicon carbide? Any current technology using silicon carbide? Silicon carbide has so many advantages, however, that the higher cost limited the market in the US. So first, let's look at the silicon carbide structures. Silicon carbide is a compound semiconductor composed of 50% of silicon and 50% of carbon. It has more than 250 polytypes due to different stacking sequence of silicon carbon bilayers along the C-axis of hexagonal close-packed system. So here are the most common structures. The number here indicates the number of silicon carbide bilayers in each unit cell. So here it shows summarize the physical property of silicon carbide and silicon. As you can see here, all silicon carbide has a higher band gap energy than the silicon. So which means silicon carbide can will have higher breakdown voltage. The higher breakdown field for silicon carbide than silicon means much thinner gypsum layer is required to hold the same voltage. Higher thermal conductivity means the device can operate at high temperature. Higher electron mobility and electron velocity means switching faster, so it can be used in high frequency device. So you can see 2H silicon carbide has the best parameter, but the problem is there's no commercial silicon carbide available. If you combine all the parameters, you will see 4H silicon carbide is the best for the high power, high frequency devices. And 6H silicon carbide is for light emitting devices. So how to make the silicon carbide? So the silicon carbide, 6H silicon carbide. So the silicon carbide is grow from the particles because there is no solution phase for silicon carbide. Physical vapor transportation is method we use to grow it. So the temperature is usually 2,500 Celsius. Precise control the temperature is the key for the specific crystal growth. So the growth rate is much slower. Basically, it's less than 1 millimeter per hour. So this is very different from the float-zone silicon. Float-zone silicon will grow at low temperature around 1400, and the growth rate is about several millimeter per minute. The silicon carbide is has super hardness. It's almost the same with the diamond sample, diamond. So the slicing and polishing will be a problem. So generally for a ball, so this takes a week to grow, and it will have something like 40 to 50 substrate from each ball. There are two types of silicon carbide substrate available. One is the semi-insulating silicon carbide. So vanadium, titanium were doped to control the resistivity of the substrate because it's hard to get a pure silicon carbide substrate. This substrate is used to grow gallium nitride IP layers for high electron mobility transistors. Another type is conductive silicon carbide. So for this type of silicon carbide, nitrogen is doped. So for here it shows a wafer. So the top view and the side view. So for each wafer, it has two sides. So one side is terminated with silicon atom, the other side is a carbon atom. So both sides have very different properties. For silicon side, for carbon side, it has some more conductivity, and the oxidation rate is faster. For silicon side, it has a better electron property. So most of the electrons are fabricated on the silicon side. So I want to add one more comment is, so for this side, for the silicon side, it has a better control, a wide range of control of nitrogen on this side. So this is very important for the IP growth. And also 4-degree offcut is necessary for the CVD, for the epitaxial process, because it will provide the nucleation site for the epitaxial growth. So once we get the epitaxial layer on silicon carbide, it will be further processed, etching on implantation, and then to get the the die cutting from the wafer and then packing final application. So it has wide applications in industry, such as EV powers, EV chargers, power grid, and also the high-speed train traction system. Other applications is not related with the electronic property of silicon carbide, such as the heat sink for the laser chips, and also based on the high index of refraction, so AR lens or AR glasses were made. I want to point out here the substrate and the IP growth. So these two parts will account for about 6% of the total product. So the high cost will limit the application in industry. Here are some questions related with SIMS. So what analysis techniques are common in silicon carbide? What's the maximum spectrum rate for silicon carbide? How to identify different artifacts in SIMS profiles? And what do they mean? What calibration and reference standard do you use for silicon carbide analysis? Silicon carbide capability on multiple N-doped, N-layer, P-layer silicon carbide IP wafers. So let's first look at the SIMS techniques. SIMS technique. So we have focused on beam. So it will start on the sample. At the same time, the different species, neutral species, negative charge species, positive charge species will be ejected from the sample surface. I want to point out most of species are neutral, so which cannot be used for the SIMS analysis. And in this case, I take the negative species as example, and the negative species was extracted from the sample and go through the mass spectrometer, then enter the detector. So there is, depending on the mode, we can scan the mass depending on their mass over charge ratio, we can get the full spectrum. Or we can raster the primary beam to get a XY image of the sample. Or we can select one mass or several mass to get the depth profile. So as I mentioned in previous slides, the most of the species are neutral. So how to improve the on yield? So the primary ion beam is implanted into the surface. Ionization only happens as the spotted species leave the surface. There's a competition for electrons as the spotted species leave the surface. The winner is determined by the electron affinity of the particle versus the electron affinity of the surface. So we can increase the electron affinity of the surface by implanting oxygen. So because the oxygen will draw electrons, so there's no electron available to neutralize the positive ions. So in this case, more positive secondary ions are formed. Or we can decrease the electron affinity of the surface by implanting cesium. So because cesium has more electrons, and then it favors the negative secondary ions formation. To summarize here, this process, so oxygen source was used to enhance the ion yield of electron positive species. In this case, boron, aluminum, vanadium, titanium, and other metals are analyzed with oxygen beam. Cesium beam enhance ion yield of electron negative species for example, nitrogen, phosphorus, arsenic, fluorine, chlorine, sulfur, and other atmospheric species were analyzed with cesium beam. Or we can use the MCS plus mode to analyze the matrix or dopants across different matrices. So in this mode, the ion variation is less sensitive to different matrices. So for this mode, we use to analyze silicon carbide compositions and any species at the interface. So SIMS do have challenges. So the quantification, SIMS must be quantified use a standard with the same elements being analyzed under the same matrix material. So standard must be analyzed under the same analytical conditions. Any change in the primary beam from the cesium to oxygen, oxygen to cesium will, or energy, or impacting angle, all this will change the ion yield. So the SIMS accuracy is determined by accuracy of the standard. NIST has standard for boron, aluminum, arsenic in silicon, which provide accuracy of plus or minus 3%. So based on those reference, we can make other implant materials. So the EAG reference material will provide accuracy of plus or minus 15% or better. So here is the concentration quantification. Basically, the concentration equals to the relative sensitivity factor times the ion intensity of interest divided by the ion intensity of a matrix. So the relative sensitivity factor is determined by measuring a standard in the matrix of interest. So the RCF will be affected by the element, by the matrix, by the primary beam, by the primary beam angle, energy, and even secondary ion sightings. But RCF will not be affected by impurity concentration within diluted range. Basically, it's less than 1% or spun rate. So European EEG material has more than 900 SIMS standard, about 41 reference material for the silicon carbide. So how to quantify the depths? So if we know two methods, if we know the peak concentration for an implant, species, in the case is phosphor. So we know the peak position, and we just put the peak depths, and then we can convert the time scale into the depth scale, or we can physically measure the crater after the SIMS measure, after the profile. Here it shows the AF image, and once we measure the crater with the profilometer, then we can convert the time scale to depth scale. So here are one example for the SIMS analysis of particles, because this is the raw material. This profile shows the nitrogen concentration is about 8E15 for sample 1, and for a second sample, so the nitrogen is about 3E18. So I want to point out nitrogen is the nitrogen concentration is the intrinsic property of the silicon particle. So it's determined by the bunch of the sample. So generally, we will measure several particles for each batch, and then get the average result. SIMS can also measure the different elements, metals in the substrate. Here it shows the result for the SIMS from SIMS, and we can get price analysis of boron, aluminum, vanadium, titanium. So one important thing for SIMS is implantation. So here is the SIMS result for nitrogen. There are questions related with what's the SIMS artifact. So here I will talk a little bit about the artifact. You can see here the very high concentration from the surface. So that's the SIMS artifact. It's not real. It's from the sample handling, mostly from the surface contamination, and also from the atmospheric soft species. I will talk this one a little bit later. And also you can see there is a bomb from the profile. So this is not artifact. This is the channeling, and you can see here that's the fluctuation, and this is not from the implantation. This is from the doped substrate, because we know our detector limit for nitrogen is around 2E15. Any nitrogen above this level is real. So this fluctuation of this wave function is due to the rotating of the wafer growth. On the right side, this is the aluminum implant standard from our lab. As usual, you can see the surface artifact that due to the sample handling or coating or whatever, and also here that's the detector limit. So it has a semi-Gaussian distribution. So SIMS can provide accurate dose distribution. I want to add a few more comments here, because for the N-type and the P-type ohm contact in the device, so usually they need a constant level of doping at least E19 to E20 level. So in that case, multiple implants are required. And one feature for silicon carbide is when you implant the species, it will not diffuse. This is different from the silicon. So we can also measure the N layer, P layer in the wafer. So we can see. So I just want to point out the growth is from the substrate to the surface. So SIMS profile from the surface to the substrate, and you can see the surface contamination or artifact, and the nitrogen, the N layer, then the P-type layer, which is the aluminum. In this layer, because only aluminum is doped, and we have the contamination for nitrogen, which is around 5E15. And this layer, the nitrogen is only doped, and we can see the contamination from the aluminum here. So I want to point out here, so this tail or even the peak at this layer interface is real. It's not artifact. So another thing I want to point out is there is the hot wall effect. This is due to the source was turned off, but the source is still hot. So it will keep doping in the background. This is only observed in the old IP process, but not now. So here are the questions related with the detection limit. So what's the lowest detection limit for nitrogen in silicon carbide? What determines the minimum dopant concentration in SIMS analysis of silicon carbide? So why the low concentration of nitrogen analysis is so important? Because for the semi-insulating crystal growth, there's always a background doping. So in the low E15 level, so accurate measure of the nitrogen in these crystals can provide feedback to the crystal growth. The second one is for high power devices, the nitrogen doping level generally lower than E16. So for 1000 voltage application, the nitrogen is around 1E16, and the dripping ladder thickness is about 10 to 12 micron. And for 10 kV, 10,000 voltage application, the nitrogen doping level should be below 3E14, and the dripping ladder should be at least 100 micron. So where the backgrounds fall. So during the SIMS analysis, atmospheric containing species such as H2O, CHX, OH, NH, CN, this species will continue to absorb on the sample surface, including the area that's being spotted and collected, even under the UHV condition. So this adsorbed species will contribute to the signal of hydrogen, carbon, nitrogen, oxygen. So this is the SIMS background. It's very important to distinguish SIMS instrument background signal from the real sample signal. So here it shows the process of the background. And as primary beam spotted the sample to create the crater, whenever the primary beam spot the center of the crater bottom, then the signal collect. So the signal has two components. One is the nitrogen from the real sample. Another one is the nitrogen from the adsorbed species, that CNNH. So how to solve this background problem? So we can improve the SIMS instrument analysis method to reduce background. If background is much lower than the real signal from the sample, then the problem is gone. Here is the depth profile we obtained. So the best nitrogen detection limit of 1E14 is achieved. To get this such low background, it takes a lot of effort for us. So I'm not going to go into the details here. So another method is measure a background, then do the subtraction. This will have larger error if the signal and background is similar. The third option is raster change. So I'm not going to talk the details here, but I just want to point out. So in the same profile, we can change the raster size and increase the beam density, and then we can collect the signal at two rasters, regular raster and the smaller raster, which is the the conclusion here is, by using the raster change, we can remove the background contribution. So here it shows the SIMS result for the raster change. This quantification is based on the smaller raster, and if we use the equation from the previous slides, we can calculate the nitrogen concentration. In this case, it's about 3.5 E15. This method was tested under different nitrogen background. for example, 2E15, 5E15, even 1E16, the Ross change method result is always, is consistent. It's within 20%. So I also want to point out for the Ross change method, it requires constant doping level. If the doping level is not constant, you cannot use the Ross change method. So here are some questions related with the SIMS capability. Can SIMS quantify the nitrogen at the interface of gate oxide and silicon carbide? Techniques for characterization of silicon carbide gate oxide interface and the techniques to look for trace level chemical contaminations. How large a wafer can do SIMS analysis without breaking the wafer and the other detection limits, similar to small coupon analysis. So it's found the interface of silicon oxide and silicon carbide has a lot of defects. Nitric oxide post-oxidation annealing is a standard industrial method to passivate the defects at the interface. So the nitrogen can be measured with SIMS. So here is the result. We can measure the whole wafer without breakage. So we modified chemical 4F SIMS machine. So here is the load log. So it's about 70 centimeter cubic. Because this load log is posed to the air, it takes hours pre-pumping, then transfer the sample into the chamber for analysis. So we always have background issue for the nitrogen analysis. And here is the result. So for the nitrogen, we have background around 2E16. So this is the after hours pumping. For the aluminum, we can get the detection limit about 2E14. So SIMS can measure the concentration of nitrogen and aluminum, and also their shape, and also the thickness. So the best detection limit will be obtained from our coupon sample. For aluminum, the detection limit will be 2E13, and for nitrogen, the best is 1E14. So with this, I will pass it to Wei for next session. Wei.
Well, thank you very much, Jack. Oh, thank you very much, Jack, for those interesting answers. They've fostered some additional questions that have been posed by our viewers for you and Peter. So let's get right. So let me see if okay. First, what is the best technology to analyze the depth profile of hydrogen content in several micron of oxide film?
Yeah, this is Peter. Yeah, I'm the manager in the SIMS group in Sunnyvale, California. Welcome everyone to the webinar. Yeah, this is a very good question. So this routine analysis for the dynamic SIMS. So we can analyze hydrogen in several micron silicon oxide or silicon carbide or silicon. We have hydrogen standard in silicon oxide, silicon carbide, and silicon, to quantify.
Okay.
One good thing for SIMS, most of the time we have the best sensitivity or the other way to say we have the best detection limit, like TPM, or for a lot of the element, PPB or even PPT level. Yeah.
Okay. Okay. Oh, PPB. Okay. Wonderful. Oh, there was another question that was regarding. They ask. Sorry about that. Let me go back. Do you use silicon matrix standards or silicon carbide matrix standards when testing silicon carbide samples?
Yeah, it's a very good question. So as Jack already mentioned, so the ion yield may be different in different metrics. So at EAG, so we always use the same metrics to quantify the silicon carbide or silicon. So we use silicon carbide standard for the silicon carbide analysis. For example, nitrogen and aluminum, the dopant or implant. So we have the nitrogen and aluminum in silicon carbide standard to quantify this. So depends on the metrics. Like a lot of times, silicon and silicon carbide are close, the quantification, but some other metrics like silicon oxide, there may be some difference or big difference. So in order to get a precise and accurate analysis, so at the EAG, so we always use the same metric standard. Yeah.
Okay. Okay. Here's another question that just came in, and I'll pose it. I'm not sure if. Hello. Could you explain how it is physically possible that one silicon carbide wafer has two different sides? I'm not sure if maybe that's a crystallographic question, but you go ahead.
So for silicon carbide, it has silicon atom and carbon atom. So no matter how you cut it through the, you cannot cut the atom. You have to cut it from the I mean the atom silicon and the carbon bond. In that case, along the C axis of the 4H silicon carbide, you have one side terminated with the silicon atom, another side with always with carbon atom. So this is the very important for IP growth, and most of electronics devices are made on the silicon side. Right now, a lot of companies try to grow the silicon carbide IP taxil on the carbon side, but there's some problem to control because the nitrogen, especially for the nitrogen, it's hard to dope the nitrogen below E16 because the nitrogen likes to bond the silicon on the carbon side. So on the silicon side, it had a wide range control of nitrogen. So most of electronics are fabricated on the silicon side.
Okay. Is the detection limit for 27 aluminum or 31 phosphorus SIMs into 4H silicon carbide wafers impacted by wafer quality or epi quality?
So most of the time, no. So we found like there's no big difference for the detection limit. But sometimes if you have a rough surface, then absorption may be different, then the detection limit may be different, but not significantly. So the best detection limit we can get is always on the smooth, shiny, polished surface. But with the rough surface or the big chunk, so it depends on the detection limit may be high. That sometimes to analyze a big chunk sample, we may need to polish, mechanical polish the sample. And also, Jack already showed we analyze some silicon carbide powder, so the detection limit in the powder may be high. Yeah.
Okay. How about device silicon carbide powered devices? What are the lateral dimensions you can go down to for the SIMS measurements you describe?
So we have different type of dynamic SIMS. We have Kamika SIMS, we have Colorable SIMS, we have ion TOF. So typical size, like for Kamika, is around 200 micron, but we can analyze a small area as small as 20 micron with the Kamika SIMS. Colorable, usually it's over 100 micron. We can go to small size, like 50 or smaller. So for ion TOF, we can go to a couple micron, like 2 micron or 3 micron, the size. But sometimes we have to trade off something like we may lose the depth resolution, or we may have high detection limit for a small area. Yeah, so it depends on what type of device. It will relate it to the surrounding area, the material at the surrounding area. The detection limit may be high. So technically, yeah, we can analyze very small, like the smallest will be 1 to 2 micron.
Okay. So let me read this. Is doping in epi layers done by ion implantation or during CVT growth? Is the accuracy of determining nitrogen or aluminum the same for ion implanted or in situ growth doping?
Yeah, you want?
Yeah, okay. So for the I mean the precision for the IP is I mean it will not change because the SIMS will not change the precision for no matter it's IP or it's implant. So but for the implant, generally we have better precision because the generally detection limit is not an issue. So for the N type and P type, both can be grow. I mean can be sorry. So for N type and P type, both methods are okay. You can dope the aluminum, nitrogen, or nitrogen when you grow the IP layer, or you can implant it. So for the silicon carbide, the problem is when you implant it, it will not diffuse. This is different from the silicon. For silicon, you implant it, you anneal it at high temperature, so the aluminum nitrogen will diffuse. The shape will be different with the profile at the without the annealing. But silicon carbide is hard. I mean the diffusion is very low. So but for the SIMS measurement, it will not affect the precision. Generally, the doping level, yeah, whenever the doping level is low, yes, because of the background contribution, it will affect the measurement. But for implantation, we have some like 10%, basically 10% of precision.
Okay.
Or something I like to add here is for the when you have different level of concentration or different dose. So why we can use one standard to quantify this, because ion yield will be constant. Most of the time, we call it the impurity level or below 1%. Like for silicon, it's 5e22, the pure silicon atomic density. So 1% is 5e20. That means below 5e20, like from E13 to 5e20, the ion yield will be constant. That's why we can use one type of standard to quantify this range. Yeah.
Okay. This one I'm going to paraphrase, but it's asking, are there limits in particle size to analyze powders via SIMS? So they're asking if SIMS can measure powders, and if so, if there's a limit to the size of the particle or the powder particle size that can be measured by SIMS.
Mm-hmm. So in order to focus the beam, so most of the time the particle size we can measure like over 100 to 200 micron, but we can analyze as small as 50 micron sometimes. Yeah. For the small one, it will depend on, I would say, yeah. But over 100 micron to 200 micron, so we're very comfortable to analyze them, and yeah.
Okay. All right. Well, I think okay. I think we'll just ask one more.
Sure. Yeah.
Okay. Well, which aspect of silicon carbide characterization do you use quad SIMS?
Yeah, that's a very good question. So we have three different type of dynamic SIMS tools. So basically based on the mass spectrometer or mass analyzer. So for the corpus SIM, the good thing is the mass switch is very fast, so it can analyze multiple elements in one profile. And also the charging compensation is better for corpus SIMs. So if there any insulating layer, like a silicon oxide or the gate oxide, so core will do a better job. And also corpus SIMs is easier to get the low energy. For example, for the gate oxide on silicon carbide, if you want to see the interface, so that will be the thin layer, depends on maybe a couple hundred angstrom. So that will be a good option for corpus SIMs to do the analysis. Of course, we developed some protocol for Kamika. We can also do some jobs, but if it go to thinner, then corpus SIMs with low energy definitely will be better. One thing for corpus SIM is so no mass resolution. So if you have any mass interference, or you want to analyze a low level or this dopant, then there may be a problem for corpus SIMs. Yeah.
Okay. Okay. Well, I think that's all the time we have for questions at this time. So I think we're going to wrap things up. So if we can move on to our next slide, please. Okay, so our experts were able to cover quite comprehensively silicon carbide of power electronics. It's this type of experience why why clients will choose EAG for this and other topical materials. However, there are other reasons to choose EAG. I think it's important to state right at the top. Another is client confidentiality, because it is core to our business. Obtaining proper results sometimes necessitates clients share sensitive information. We safeguard this information with formal non-disclosure agreements. We are a global leader for materials testing services with a broad range of instruments and expertise that leaves us poised to take on even the most challenging material and engineering related issues. And with over 2,500 instruments available to us, we can do so in a timely fashion. At EAG, we have various certifications, accreditations, and regulatory approvals and licenses to support our clients' needs and in a professional manner. EAG is ready to solve your materials and engineering related product problems. Now I'd like to turn things back over to Dina for some closing thoughts. Next slide.
Thank you to our experts, and thank you to everyone for attending today's Ask the Expert webinar. If we didn't get to your question today, we will be following up with you soon. If you have any other questions, please send them to the email address listed on the screen. As a reminder, once you leave today's webinar, you will receive a quick 5-question survey, and we would really appreciate your feedback. On behalf of Eurofins EEG Laboratories, our experts, and our moderator, thank you for joining us and have a great rest of your day.
Okay.